Reminder that if you're gone on Kearney Cats, go to the AP Calculus page, go to Find Me or AP Calculus or whatever. I'm sure you know how to get to there. And the class videos are in there, and then the homework. Try to keep up with that. That's down the side there. Of course, you can always text somebody that's in class and ask them as well. But I try to keep that updated. If you lose your assignment sheet, there's another copy of the assignment sheet down here as well. So, so today we have, well, I've kind of got the weekly. I'm hoping to keep this updated too. But section 1.3 is what we're going to be covering today. We're going to do some review and do some trig stuff. We got our quiz on Thursday. Okay, so the quiz is coming up on Thursday. So let's take a look at your homework questions. And I didn't see this on there too much, but there were a number of people that have either come in to ask me or the other class seemed to ask about this more. Now, you know, the other class maybe isn't quite as sharp as you guys. Don't tell them I said that. But so, for example, number 2, all right, and I was a little bit surprised, I guess, and maybe I just didn't emphasize this enough. And it said that this is a function b, and they tell you that it has a y-intercept at 3, and then it tells you at negative pi, which would be about over here somewhere, it has an x-intercept. So we have a y-intercept at 3 and an x-intercept at negative pi. And then they ask you what's b of 0. Now what I want to remind you of is, and I said this yesterday, but I said a lot of things yesterday, so it kind of maybe got lost in the shuffle, is in this class, if we have the point 4, 8, we won't write it that way very often. Usually we'll write f of 4 equals 8. Now those two mean exactly the same thing. They both give you a point on the graph, okay? And this means the x value is 4, and this means the y value is 8, or the input and the output, okay? And so when they tell me that the y-intercept is 3, what they're really telling me is the point 0, 3. Or in function notation, they're telling me that b of 0 equals 3, right? So when they told me that I had a y-intercept of this, they were telling me that. And then they ask you what's b of negative pi, and again, when they give me an x-intercept, they're really telling me negative pi, they're really telling me at that point. And so that's the same way of saying b of negative pi equals 0, okay? So that was 2. Now, when you get into 4 then, 4 talked about roots. And again, I think I made that comment about my Algebra 1B class, and roots grow under the ground, and the x-axis is like the ground and all that stuff. But it talks about roots. Roots are what? X-intercepts. Another way of saying that is roots are where the function what? Crosses the x-axis. Another way of saying that is where the outputs are 0. So a lot of people say a root is where it's 0. What do you mean it's 0? You mean where the outputs are 0, the y values are 0. So when you're asked for roots, that's like answering this question, right? That we will be doing that a lot this year. Where does the function equal 0? And that's usually solving an equation. They're not something you can plug in, but it's solving that equation. Where does a function have an output of 0? Finding the inputs where that happens. Well, so if you look at that, was on question 4. I think they told you that big F of 0 was what, negative 2 on question 4? And they told you big F of 2 was 0. Well, which one of those is a root? That one, right? That's a root at 2. And whenever we ask where is a root, or where is a local max, or where is a local min, we want the x coordinate. So where is a root? It's at 2. At x equals 2 is where that root is. Okay, so I had a number of questions about that. A little bit surprised, but really as I thought about it, I thought, well, maybe I just didn't emphasize that enough. So a lot of this quiz, this first quiz, to be honest, we're still not doing calculus, right? I mean, this is all pre-calculus stuff. This is all algebra. But it's the stuff from pre-calculus and the stuff from algebra that we really need to understand and be able to work with when we get into the calculus stuff. I mean, so that's really what this first stuff is. So we need to be able to read graphs, and we need to be able to do all that. Now, I have decided I'm going to let you use your calculator on the quiz, because I am going to ask you, one of the things I want you to be able to do is do a graph, trace, find the maximum, find different points on the graph, be able to describe what the graph's talking about and doing, kind of like some of the questions you had here. So I am going, because just on this first quiz, I'm not going to expect you to memorize these different types of graphs. Now, that's one of the things we're going to be working on today. And by our next quiz, you may have to. It may be helpful to have memorized what some of these graphs look like, but not for this first one. So I'm going to let you use your calculators. Okay, what was another one? What was another one? I know we got 60. We're going to do that one. I know we got 69. We got to do that one. What were some other ones we had up there that people wanted to see? 55 was one. Okay, so 55, is that the one about the volume of the tank? Okay, so we've got this half of a sphere. It's got some water in it down here. Okay, all right. Now, one of the things you probably need for this would be to know the volume of a sphere. Now, if on the quiz I ask you a question like this, I would give you that. I don't expect you to know that. Okay, so hopefully you noticed that you would probably need it, I think, for part B. And the volume of a sphere is 4/3 pi r cubed. But since it's only half of a sphere, it would be 2/3 pi r cubed. Okay? Now, you've got this formula V of D. Now, this is one of the things I want you to be able to do on the quiz. If I describe a situation and tell you what the inputs and outputs are as a function in function notation, I want you to be able to answer questions using that notation. All right? So, V of D is, we don't know what the equation is, but D is the depth of the liquid. Okay, so D would be this depth right here, and V then the volume. So when they ask for V of 0 in part A, what are they saying? What are they asking for? Volume when the depth is 0, right? They want the volume when the depth is 0. Well, of course, that would be 0. There's no volume. Okay? And when they ask for V of 10, they want the volume when the depth is 10, right? Well, this whole thing is a height of 10. So that means it's full, right? So what's the volume when it's full? Well, that would be this formula for half of a sphere. So it'd be 10 cubed is 1,000 times 2/3. That'd be 2,000 pi over 3. That would be the volume. I would give you that formula then. Okay? So that's part B. And then what was part C, the graph? Which of those graphs describe this? Okay, what'd you say? C. It couldn't be A because A doesn't start down at the origin. We already established that V of 0 equals 0, so that's the point 0, 0. So it's got to start down at the origin. But then the other three all increase. And as this fills up, right, as D increases, V is going to increase. But how do you know the concavity? Why is it the one that is concave up? Why? Yeah, but I mean, they're all, I mean, what are your choices? You got that choice, and you got another one that goes up like that, right? The volume, as D increases, the volume's going to increase as it rises up. Those all increase.
The slope of the, I guess, the edges of the semi-sphere, they don't necessarily allow for a greater depth as volume increases because the walls are becoming gradually more steep. So that's why the C for gradual increase, or accelerated increase in volume as the depth.
So if this was 1 foot right here of water, right, that's a certain amount of volume. If we added another foot of depth, what could you tell me about that chunk of water we just added?
More volume.
It's more volume than the other chunk of water. Remember we were doing that with trapezoid? We talked about that chunk of area, right? So what's happening is we have a foot of depth, we have a certain volume. We add another foot of depth, we're going to add more volume because those, like you said, the sides of that are expanding. And so we've got a bigger space. And a bigger space and a bigger space. So the volume is going to be not only going up, but at an increasing rate. And so therefore it has to be concave up. Has to be concave up. So you need to be able to communicate that. A picture along with some words can be helpful in explaining those things. Okay? Is that all of 55 then? All right, what else? 23. Is that the one about the periodic? Okay, now in the periodic function, they tell you the period is 7, and they tell you that it was a t of 0 is 3. Now again, what I would do on one like this is I would draw myself a picture. Okay, as soon as I'm given this information, okay, 1, 2, okay, that's a terrible graph. Okay, so as soon as I see t of 0 equals 3, that's a point. I'm going to plot that point, and graphs, I think, are a good way to look at this. So they asked me now I know I'm backing up here a little bit. Before we talk about 23, we might as well talk about 21, 22. So what do you have for t of 7? 3. Because if you go over here 7, that's what periodic means. Now, this was a little different way of thinking about periodic functions than what we're used to. You're used to periodic functions, oh, sine graph. Yeah, it repeats. I mean, but our depth of knowledge of periodic functions is not that deep, right now. I mean, yeah, they repeat their values. This is another way of thinking about it. So if we can think about it in multiple different ways, that increases how well we understand the concept of periodic. So every 7, it's got to repeat. So at 14 here, it's got to repeat that again. We don't know what's going on in between there, but we know it's got to keep repeating. At negative 7, we have to get 3. And at negative 14, we got to get 3 again. Okay? So that just took care of parts A and B, right? It'll be 3. All right, then they throw this one at you. T of negative 30. Explain why this has to equal this. And these are some of the kinds of questions that are going to be on the quiz. Okay? Explain and be able to look at this in various ways. Okay? Well, tell me out here. Now, I don't quite have room, so here's T of 40 out here. Now, is that a multiple of 7? No. So do we know what that output is? No, we have no idea. We have no idea what this output is, and we have no idea what this output is. But you know what? It doesn't matter. All we're trying to answer is what? They're the same. That's all we're trying to do, right? So, somebody want to go from here? Yes, sir.
Well, they're negative 30 and 40.
Oh, let me get that
have an interval of 70 between them, and 70 is a multiple of 7. So
okay.
whatever the value of that is, it'll also be the same value of that, so we'll repeat it 10 times.
So this value, I don't know, might be there. Who knows what it is, right? But you're telling me from here to here is a distance of 70, which is, say it again, how many? 10 periods, right? 10 periods. So we don't know, but we could count it backwards. 33, 26, 19, 12, 5, negative 2. You know, I mean, we could actually go negative 9, negative 16, negative, well, I went this far with that, negative 23, negative 30. There it is. It would land every 7. Okay? But, yeah, and that would be our explanation. That's a distance of 70. That's 10 periods. It's going to repeat that output, whatever it is. We don't know what it is, but we know those will be equal. Again, like I said yesterday, when you see t of negative 30, I would hope you think output. That's an output on the graph. That's a y value on the graph. T of 40, that's a y value on the graph. Those two y values are going to be the same because they're 10 periods apart. Okay, very good. Very good, very good. Next. Anything other than 60 and 69? What was the one about the child's temperature? 56. Now that might have been an easy one, but let's say this is 1 over here. This is negative 1 over here. Now the reason, it says the child's temperature has been increasing for 2 hours, but not as much since we gave her the medicine an hour ago. And they told you that they wanted t equals 0 to be when they gave her the medicine. So here's her temperature when they gave her the medicine. What's this graph have to do from here to 1? It has to increase, and what else? Slow down. Now, I would guess it's going to be a curve. Now, I'm not so sure it would have to be a curve, but that's how I drew it. Did anybody else draw it where it wasn't a curve? Okay, so we'll talk about that here in a second. But I would graph it as concave down. It's still going up, but not as fast as it was before. Now, what might be a reasonable guess at what it did for the hour before? Yeah, like concave up, maybe. Like her temperature was rising and rising and rising faster and faster. We gave her the medicine, and then it started to slow down. So that could be reasonable. But wouldn't this also be reasonable? If somebody had a graph like this, and then a graph like that, 2 line segments, would that be reasonable? Would that still answer that question? It just said that for the last hour, it's not rising as fast as it was the previous hour. Okay? So that could be reasonable. But I like getting the concavity kind of piece in there. Okay? So something like that. So that's why it goes from negative 1 to 1. Now in part B it says, what's the significance? See, this is the kind of question I might ask, so I want to make sure, a big part of this quiz is, can you read the math notation? Can you understand the question, what it's asking? I mean, really, that's a big part of it. So it says, what's the significance that the graph is increasing from negative 1 to 1? Yeah, I mean, it's that simple. The temperature's rising. I mean, so when you read a question like that, you think it's got to be some big fancy explanation. No, the temperature's rising from negative 1 to 1. That's why the graph's going up. Okay? And then what was the other one? Did it say concave down in part C? Or, it literally said concave down, didn't it? So, you wonder about this straight line thing. But since it's concave down, well, it's because it's not rising as fast. It's not rising as fast. The rate that it's rising is starting to slow down. Okay. Onward. What else? Anything other than 60? I'm trying to think what else we talked about in the other time. Oh, I know what I wanted to talk about. I want to talk a little bit about 7 through 10. Did we do all those 7 through 10? Okay. Now, on your this would be one, and I was a little unsure of this when I signed this yesterday. What do they call it? G? Okay. One of the types of graphs we're going to talk about today is one just like this. Now, later in the year, it would be my hope that we would be able to draw a quick sketch of this. That when we look at that, we would at least know some basic things about it. Okay? Right now for Thursday's quiz, not so much. So if you went ahead and graphed this on your graphing calculator, that would be fun. Okay? Now, let me explain to you some things that a person could know about this. Number one, if we FOIL this all out, what's the high power going to be? So this is a cubic graph, and my hope will be, especially after today, that we understand that cubic graphs tend to have that kind of a shape. Okay? Or if there's a negative in front of it, they could have that sort of a shape. The tails would go the other way. All right? Now, also, I know something about the roots of this equation. Remember, the roots are where the output is 0. Where would the output be 0 in this? At negative 1 and at 2, right? You spend a lot of time in algebra class solving these kinds of equations, right? Factoring them and so forth. So this graph is going to cross right there at negative 1 and right there at 2. Since the leading coefficient is going to be positive, I know it's going to come up like this. Now another thing I know about this is since this is a squared, that's what we call a double root. And whenever you get a squared like that, it means the graph, when it comes down, it just touches and bounces right back up. So if you were to graph that on your calculator, you would get something very similar to that. Okay? And that's just because I know about cubic functions, I know about roots, I know about those kind of things. Okay? And so I can do that. So now when I graph it on my calculator, I already know kind of what I should expect to get. Helps me set the window and all that kind of stuff. All right. So now I can answer some of those questions. Is it even and is it odd? Now I helped some of you yesterday, and we didn't do graphs. Some of you, I said, well, you could plug in opposites. Remember we said for an even function, it's opposites in, same out. We also said it has to have that y-axis symmetry. Well, this graph clearly doesn't. You can't fold this graph, right? So you could say it, if I ask you this question, you could answer it based on that. It's not, it doesn't have y-axis symmetry, it's not even. We talked about opposites in, opposites out for odd functions. Okay, we also talked about origin symmetry. Now, origin symmetry is a little harder to explain because it's not really a fold. I usually do it this way. Opposites in, same out mean if I go over here and up, that means I have to go over here and up the same amount. Well, that doesn't obviously happen. A way to describe opposite in, opposite out is to do this. If I go over here and up to here, that means I'd have to go over here and down to there. That doesn't happen either. That's opposite in, opposites out. Okay? So that's a good way to explain origin symmetries with a graph. Yes, sir? Origin symmetry, if you want to look for a fold, would be right there. Okay? in that diagonal line. Or you could fold on the Y, fold on the X, kind of a thing. Okay? So if you're looking for a symmetry, you can use that as your symmetry. Okay? Because you can see if I come here and here, then I would go here and here, and they would be on those lines. Okay? Now, or you can plug points in. So if I put a 3 into this one, I'd get 4 times 1 squared, that'd be 4. If I put a negative 3 in here, I'd get negative 2. Negative 3 minus 2 is negative 5, squared is 25. I get negative 2 times 25, which is 50. Negative. So there I put opposites in, and I didn't get the same out, and I didn't get opposites out. So I didn't get either one, so it's got to be neither. So those are all different ways we can talk about even and odd functions. Okay? And then, of course, we've already done a bunch with periodic, and then it asks about increasing and that kind of stuff. But you can trace on your calculator on the quiz. So on the quiz, I would say put that into your calculator, trace, answer those questions based on that kind of a thing. All right, let's go to number 60. Is that the one with completing the square? Okay, since that's the part that probably hung up a lot of you, there would be a way to do this one without completing the square. Because they were kind of nice to you, they told you that, was it F? Which one? Was F equal to x squared? Okay, and what was the other one called? G. And G was x squared plus 4x plus 3, right? Now they told you in part A, they said explain why G was equal to f of, what was it, x plus 2 minus 1. Now here's one way you could have done this without completing the square. Since they told you this information, this is something that we're going to be reviewing later also. If I ask you what's f of 3, what do? And you had an equation like this, what would you do? You put 3 in for x, right? You put 3 in for x. Okay? So if I ask you for f of x plus 2, what could you do? Put x plus 2 in for x. Are you with me there? If f of 3 means put a 3 in for x, then f of x plus 2 has to mean put an x plus 2 in for x. So I could take the f function and I could put an x plus 2 right there in for x. So I would have x plus 2 squared and then minus 1. Now, not something you have to do for the quiz on Thursday, but something we'll be seeing a lot of later on. Now I can FOIL this out, which would be x squared plus 4x plus 4 when I FOIL, minus 1, which is x squared plus 4x plus 3. And there I have just showed that g of x, which is this, is equal to that, without doing any completing the square. Now, with that said, I would rather us think of it as completing the square, because normally we're not given this information. Okay, normally we don't have this information. Here's why we would want to be able to complete the square. Not going to have to complete the square Thursday, okay, on the quiz, all right? What you will have to do on the quiz is if I give you a deal like this, I might say, hey, tell me what, and I think this was part B, how does a G graph compare to the F graph? What would you say? Shifted, left 2, down 1. Very simple. How is a G graph related to the F graph? It's shifted, it's the F graph shifted left 2 and down 1. Okay? Pretty good bet there's going to be a question something like that. Okay? But normally we don't have this down here. So let's just look at this for a minute, and let's say it was a no calculator thing, and I wanted to graph this. Now I know this is a basic parabola. I mean, that's an easy one. It goes through 0, 0, 1, 1, negative 1, 1. If I put in 2, I get 4. Negative 2, I get 4, right? Just a basic parabola. And I'd like to graph this without a calculator. Well, it's pretty hard to graph. I could plot some points. How do you find the vertex? Maybe you remember from algebra that the vertex is actually negative b over 2a. Maybe you remember that. Maybe you don't. That could be helpful if you do remember that. Okay? But here's another way we can do it. We can complete the square. Well, here, how do you do that in algebra? Well, you do this. You leave yourself a blank. Now, everybody remember? What do we do to complete the square? Half of 4 is 2, and you square it, which is 4. Now, we can't just add 4 to this side without changing things, so we got to take away 4 to offset that. We could add 4 to the other side, but I don't want to do that because that's my g of x side. I don't want to add 4 over there. So I'll add 4 to that side, but then I'll take away 4 to offset it. Okay, now these three right here make what? X plus 2 quantity squared. And then 3 minus 4 is minus 1. And sure enough, that's what we got right there. We've got the G graph is just a plain old x squared graph shifted 2 to the left and down 1. And then I could very easily graph that. I could say, okay, that's shifted 2 left, down 1, and I go over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4, you know. And then there I would have my graph. So by completing the square, that's one way I can do that. How many times that comes up this year, not done. Not a huge deal. But it's just like a lot of algebra and tricks that are good to know. When they pop up, it's sure nice to know them so you don't have to get hung up on those. We got enough calculus things to get hung up on without, But it's gonna happen. I mean, it's gonna happen. You're gonna get into some of those. All right. Last one, number 69, I believe, right? All right. They tell us here that f of, what was it? F of 0, 1. Oh, G. G is always concave down. They tell us that. And what points they tell us? 0 to 10, it's always concave down. And G of 1 is 4. And G of 5 is 2. So we know, so if this is a G graph, if we plug in a 1, we get out 4. And if we plug in a 5, we get out 2. Now, if you didn't draw a picture of this, that's where you're mistaken, right? I mean, as soon as they told me those points, the first thing I think of is draw a picture and plot. Okay? And G is always concave down from 0 to 10. So in part A, they want us to say, how do we know then that G of 3 is greater than 3? Now this is a lot about notation and language. Understanding what's being asked. When you see G of 3, you should think what? The output when x equals 3, right? That means when you see G of 3, you should think y value. Y value. So when x is 3, the y value, we're trying to show that the y value has to be greater than 3. So over here, 1, 2, 3, 1, 2, 3. Now there's an output of 3. But we're supposed to show that that output is more than 3. Somebody got something? Anyone to help us here? Give it a shot.
Well, just the way it is right now, it's just a line.
That's a big secret to this right there. Recognizing that that point is on a line. If you go down 1, you go over 2, down 1, over 2. Right now, that point is on the line in between. Okay, keep going.
And so it has to be, if the point y value is any greater than 3, then it will make it into a concave down pattern even ever so slightly.
Okay? If this graph is going to touch here, and it's going to be concave down, it can't dip below this line, can it? I mean, what's the concavity of a line? There isn't any, right? It's not concave up or down, okay? There's no concavity. If this graph was going to try to be concave down, is there any way it could get to this point? Not without turning and going concave up, right? It can't happen. It's got to bend up. I mean, it's got to not bend up, but it's got to do that, right? To be concave down. So right here, the y value's got to be above 3. It's got to be. Okay? So there you go. I mean, that picture, along with some words, would be how you would explain that. Because the G of 3 equals 3 is on a line between those first 2 points. And so to be concave down, it's got to bend above that. So the output G of 3's got to be greater than 3. Now, part B asks basically the same question, but just in a little different way. It says find a number L such that G of 4 is greater than that number. Again, G of 4 is the y value at 4. So we come over here to 4. I would use that same line. Oops. What is that y value right there on that line? Wouldn't that have to be 2.5 on that line? So if this is going to bend down, doesn't g of 4 have to be greater than 2.5? Now, right? I mean, that would be your cutoff. It couldn't be 2.6 because it might just barely curve. I mean, it might almost be straight. If you looked at it with the naked eye, it's still concave down, but it looks straight. So it could just skirt along that line and still be concave down and just barely be above 2.5. But g of 4's got to be greater than 2.5. Now, is that your only possible answer, though? What else would work? What else would work for L here? Negative 1,000? Anything below 2.5 would work. It says find a number L such that the y value at 4 is always bigger than that. Well, we just found the absolute biggest it could be is right there at 2.5. Well, actually, it couldn't be 2.5, but it's got to be greater than 2.5. So any number below 2.5 would work for L. Okay, any number below 2.5. But it just said find a number L. So you could put 0, could put negative 10, whatever. As long as it's less than, it's 2.5 or less. Okay? So there you go. So that's kind of your first introduction to that kind of language and a question being asked that way. Okay? All right. Anything else before we leave this section? Because there's a lot of stuff in here. I mean, all that stuff's important, all that notation and language and so forth. It sounds like we got a lot. All right. My plan is to give you a lot of work time today on the homework. And so if you've got some questions lingering still from this or from section 1.1 or whatever, feel free to ask those. But let's go ahead and talk about the next section. So if you turn to section 1.3, that next page there, we'll take a look at this. All right, so you might get your calculators out because we're probably going to graph a few of these things, and I'll probably go ahead and find a presenter here. Oh, Carrie, weren't you just presenter yesterday? Okay, we need a new presenter. She just got to do it yesterday. All right, who feels lucky? Joe, all right. Error, what? Oh, sorry, Joe. All right. Nate. Why? What? Everybody's logged in. Okay, what's the problem? Oh, that's Carrie. Well, it's Carrie's is where I don't know. It's bent on Carrie being the presenter today, so I guess we'll have to go with that. A second chance. Why did she screw it up yesterday? I don't remember. I don't remember that. All right. So, okay. So on page 24, what we have here in section 3 is a review of different types of functions. Okay, so all right. So specifically, what their graphs are like, but we want to be able to understand questions about domain and range and all that stuff. And these are they call them elementary functions, okay? And they're elementary in the sense that they're made up of basic elements. Elementary. One calculus class one year, I used to say basic a lot. And they got mad at me because that made it sound like it was supposed to be easy, and it wasn't easy. And so, when elementary, same thing. So I try to be careful on the words that I choose. But fundamental, maybe that should be the thing that we do. But these are the functions that we really need to know how to work with, and without a calculator, and even with a calculator, you're going to see on some of these that sometimes a calculator is not all it's cracked up to be. If you go in to graph a function, if your window's set wrong, you don't see it all, or you might not see any of it. And you've got to understand what's going on, because I won't bail you out, especially on a quiz or something. You've got to be able to know enough about that domain and range and what it's supposed to look like so that you can set a proper window and see the graph the way it should be seen. All right, so even with the calculator, it's important to understand these things. All right, so the first one we're going to talk about is polynomial. Okay, polynomial functions are the most friendly type of functions we can have. I mean, they don't have any domain issues. Polynomials, you can plug anything in. And the range is fairly easy, and they're nice and smooth, and nothing weird happens in them at all. They're just the easiest we can have. Now, the first one would be like a line, like mx plus b, right? Positive slope, it's going to go up. Negative slope, it's going to go down. Of course, you could get horizontal and vertical. Vertical wouldn't be a function. But that's polynomial. That's linear. Okay, whoops, I should write linear. Okay, so linear. Then you've got quadratic. Second degree. Like ax squared plus bx plus c. Now, I'm not going to write all that every time. But what kind of picture do those make? Quadratic equation. Parabolas. Now, parabolas are either going to open up or they're going to open down. How do you tell if they open up or down? The a, right? The leading coefficient. Now, that kind of makes sense because look at linear. The leading coefficient, of course, we know that to be the slope, right? But if the leading coefficient is positive, it goes up, and if the leading coefficient is negative, it goes down. And so it works with linear too. But opens up or opens down. The tails go the same direction. Now, with linear, the tails go opposite directions. Here, they go the same direction. Now, you get into a cubic. We already talked about that a little bit earlier. That would be like an x cubed. Now, again, polynomial functions always have to have whole number powers. We can't have like x to the 1/2 or anything like that to be a polynomial. We can't have negative powers. Okay, that's going to be something else. All right. So a cubic is going to look like this. Okay. A cubic could have as many as 2 humps, local max, local min kind of thing. It could have as many as 3 roots, right? A cubic could have 3 roots. Now, it might have fewer than that. A cubic could just go like that, and right? It might just have 1 root. It might just cross the x-axis 1 time. It could just have 3. It could have 2. We talked about 1 a minute ago where it came down and just touched the x-axis. Okay, you're going to have some questions in your homework about cubic functions and various functions. Now, one thing you notice is the odd powers always have the tails going opposite. So 3rd degree, 5th degree, 7th degree, 9th degree, on and on and on. They would all have this same property. Now, the only thing that changes is the higher the power, the more humps you might get. Like if you have a 5th degree could go up and do that. It could have 1, 2, 3, 4 humps. It could actually cross the x-axis 1, 2, 3, 4, 5 times if it was a 5th degree. Okay, we won't even talk about having a name for that. But okay, so odd power polynomials have certain properties. Okay, even number like a quartic, this would be a 4th degree, or you could even go up to a 6th degree or whatever. But a 4th degree could potentially have 3 humps. It could have 1, 2, 3, 4 roots. So the number of roots matches the number of the power. But the tails, notice, go the same direction, just like they do on an x squared. Now, it's possible it doesn't have 3 humps. It could just look like a parabola. X to the 4th could just, you might think it's a parabola, but it's actually an x to the 4th. Okay, so it might only have 1. Same thing with a cubic, or a 5th degree. Might have all those, but a 5th degree could look like a 3rd degree. Okay? All right. So that's going to have some bearing on how many roots it has and what its outputs look like and so forth. So in the homework, they're going to ask you some questions about those kind of things. But again, polynomials always have all reals for the domain. You know, they're nice and smooth, no weird things going on. Okay, let's talk about rational. Rational functions. Now, we're not going to get into these very much, but you might have to graph one on your calculator, and you should know a little bit about it, but later on it's going to become more important when we get into talking about limits and stuff later. So here, we'll just do a couple quick examples. Let's do x minus 1 over x minus 2, x plus 3. Let's do that function. Rational means a polynomial divided by another polynomial. Okay? Now, what domain issues do you have there? X could not equal 2 or negative 3, could, because you'd be dividing by 0. Okay? So you've got some domain issues, some places where it's undefined. Now what happens on the graph? What do you think happens at those places? So asymptotes, vertical asymptotes. Okay? Well, that's one of the possibilities anyway. Let's go ahead and graph this one, oh Miss Presenter. And anybody else if you want to. Yeah, I'd get rid of those. Oops. Hit escape there. Yeah, I would hit a left or hit that control divide by would be a good quick way to get a fraction. Not that you'd have to do it anyway. So x minus 1 on top. Okay. Perfect. Okay, why don't you go to your window and just do a zoom standard. That way everybody's kind of looking at the same thing. So window, this one of the things I want you to be able to do is set a window. Go ahead and go into an equation, draw a graph, set a window. Okay, now, what's that undefined? Does everybody have that on there? I don't know if that's left over from something else. I don't know. I don't know why that's there. Okay, anyway, so you can kind of see the vertical asymptotes. Sure enough, at 2 and negative 3, looks like there's vertical asymptotes, which is where this would be undefined. Okay, now, knowing about these functions, knowing that that would be a problem right there, there's some other things we'll learn about this, knowing that this is a horizontal asymptote right here at the x-axis. It's coming down here, getting real close, not touching it. Now, one thing people misunderstood about a horizontal asymptote, it can cross. You can cross a horizontal asymptote. Right here, it crosses the x-axis, right? Horizontal asymptote just means way out at infinity, it's getting closer and closer to that value. Okay? Now, vertical asymptote you would never cross because vertical asymptote means it's undefined. There is no output there. So it couldn't cross it, otherwise it would be an output. Okay? All right, so that's what that looks like. So whenever you get a rational function, you get all kinds of weird, crazy things going on because you got these asymptotes and things happening. Okay? Now, let's do another one. You can go ahead and delete that one out. Let's do this one. If we had, let's do x squared minus 1 and x minus 2 over x minus 2 x plus 3. Okay? Now again, what domain issues do we have? Okay, so x cannot equal 2 or negative 3. Now, does anybody have something else that they are thinking about when they look at that function there? One would be okay because it would give you 0, but 0 on top's okay, right? Because 0 divided by something is just 0. What about those x minus 2s? Okay, now, hold that thought. But if I was to take x minus 2 and cancel it, I'd end up with this, right? Okay? Now, why don't you go ahead, go ahead and enter that. Okay? Oh. We're getting area. Somewhere you probably did an area thing, and that's still on there. Wonder how we get rid of that. Yeah, that was from that problem we were doing the other day, right? Okay, well, we'll just ignore it. Pretend it's something. Okay. So, now hold on a minute here. Didn't we just say that we should have a problem at 2 and negative 3? Right? Like a vertical asymptote? Now, it looks like we do at negative 3, right? That's going up, 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 up. Looks like we do. But I'm not seeing anything here at 2 that's a problem. Go on to F2. Go into F2 and type this one in. And now, are you imagining we're going to get exactly the same graph? Right? In Algebra 2, we learned that if you cancel those out, this is the same, right? It's equal. Okay, so let's go ahead and let's do that. Let's cancel those out. And go ahead and graph it. Okay, now it's in red. Now it graphed right on top. So that looked okay, didn't it? Okay, now go ahead and go to trace. And let's just see what's going on at 2. So go to trace, choose graph trace, type in a 2. Now notice, hit your left arrow one time. Okay, here we are with this blue trace point, and we're almost at 2. Now go ahead and hit the right arrow one time. Look what it does. What's happening right there? There's a hole. There's a hole in that graph. Now, we can't see those on our graphing calculator. It won't put a hole there. But there is a hole in that graph. Because clearly, in this function, we cannot let x be 2. Right? Because we'll be dividing by 0. It'll be 0 divided by 0. But that's still a problem. But in this one, is 2 a problem? Now, the way you can trace on 2 different graphs on the calculator, Carrie, hit the up arrow. Right now, we're on the blue graph, F1. Hit the up arrow. Now hit the right arrow. Now she's on F2, the red graph. And 2 is giving us 0.6 on that one. Well, if I put a 2 in here, 2 squared is 4, minus 1 is 3. 2 plus 3 is 5, 3/5, which is 0.6. So on this graph, 2 has an output of 0.6. On this graph, 2 does not have an output. So in Algebra 2, Mrs. Andreessen was kind of keeping a secret from you. When she told you that this was the same as this, that's not really true. They're the same everywhere except when x is 2. When x is 2, this one is undefined. This one has an output. Okay? So anyway, a little bit beyond what we need to be able to do, but I want you to be able to trace, look at it, see some of the strange things. So just because it's undefined doesn't always mean it's a vertical asymptote. Yes?
So could you take any other equation that say, like if the original equation was x squared minus 1 over x plus 3, couldn't you just put in the, say like x minus 2, or if you could put in x minus 4 on the top and bottom and then not mess it up for
Yes.
4, but it's still equal to the same equation?
Everything else would be the same except at 4. So they wouldn't be the same. No, if you took this equation, put an x minus 4 and x minus 4 down here, you now changed it at 4. There'd be a hole there. Okay? Now, another little secret about this graph. We're not seeing the whole thing. This is another thing that a person, when they become more familiar with these types of graphs, says, wait a minute, I got a vertical asymptote here at 3. How come isn't there another piece of this graph? So go to zoom in the window, go to zoom, and zoom out. And ask for the center, just right there is fine. Hit enter. Uh-oh, see that down there? Okay, hit enter again. Zoom out. Okay, that's good enough. Now, see what's going on? So we got this vertical asymptote here, and we also have something that's called a slant asymptote or an oblique asymptote right here. There's an oblique asymptote right here. Now we'll get into that a little more when we get into limits and stuff later on. But rational functions just have a lot of goofy, weird things that happen. Polynomials are awesome. Nothing weird happens with those. But these rational functions, kind of strange. Okay, Carrie, go ahead and clear those out, and we'll move along here as we get to take notes and she has to miss what we got. Okay, the next one I want to talk about is exponential. Okay, exponential functions. Now, exponential functions are the type where you have a number and then in the base, and then x is up in the power. Okay? Now, probably easiest here to show you some from your book. Your book does a pretty nice job here of showing you some pictures. Okay, those are exponential functions. Now, a normal exponential function comes in like this, crosses at 1, and goes up. 2 to the x, e to the x, 4 to the x. Those are all exponential functions. So if you want to sketch a few of those in your notes, that wouldn't be a bad idea. Okay? Now, if you have a power that's less than 1, like 1/2 to the x power, then you get this kind of like exponential decay, if you've studied that in science at all. You got exponential growth, here you got exponential decay. Now, they both have horizontal asymptotes at the x-axis. And, of course, 1 to anything is just 1, so that would just be a horizontal line. But these exponential, now you can never have a negative base either. You can never have a negative base. Just like with logarithms, we can't have a negative base. So if you had a negative base, then if you tried to raise that, say, to the 1/2 power, well, that's square root. We can't do square root of negative. So all kinds of weird things happen if you have a negative base. But, okay, so fractional powers less than 1, the exponential does this. Powers base is greater than 1, it does that. Okay, if you change the base, it changes kind of how steep, but it always goes through 1. Because anything to the 0 power is 1. Okay, so those are exponential functions. All right, next we have logarithmic functions. So again, that'd be log, base, you know, like that. Now the one we usually use is base e, so natural log. Okay, now, again, they're in your book. I'll just have you draw a couple of them. Here's what. Now, these are inverses. Exponentials and logs are inverses. They're like mirror images. Okay? But here's your basic logs. These 3 right here. Like, here's ln right in the middle. There's log base 2. There's log base 4. Now, you can see they're kind of inverses of exponentials. Exponentials go through 0, 1. These go through 1, 0. Exponentials have the x-axis as a horizontal asymptote. These have the y-axis as a vertical asymptote. So they come down here like this. Now, if you change the base to what we hardly ever see, you have a fractional base on a log, it would do this. Now, these they kind of level off. They never really level off, though. They increase the whole time, but they increase very, very slowly out there. Okay? Now, for some reason, this is the one we have the most trouble remembering. I don't know about the most trouble. It's probably the one we're used to working with the least. And they seem to like to ask this on the AP Calc test. Here's a classic question on the AP Calc test. Well, there's some calculus part that we don't know about. We've already talked about slopes a little bit, right? And there'll be a question where they'll give you a function and they'll ask you where that function is decreasing. Well, it's decreasing when its slopes are negative, right? When its slopes are negative. So then they give you the function to describe the slopes, and it happens to be this function right here. Okay? So what the question, once you get through all the calculus stuff, which we'll learn later, basically the question comes down to where is ln of x minus 2 negative? Right? Where is ln of x minus 2 negative? And this is always in a no calculator type question. Well, how do you answer that question? Well, you have to know about natural log graphs. And of course, this is a natural log graph with what happened to it? 2 to the right. See, that's why it's important to know about this shifting. So, you have to know what the basic natural log graph looks like. Now, what did we just say? What's it look like? Well, it goes through what? 1, 0. Well, this one shifted 2 to the right, so it's going to go through 3, 0. Its vertical asymptote was on the y-axis normally. Where is it now? 2 to the right. So the vertical asymptote is right here. So this graph that they're asking me about looks like this. Now the question is, where is it negative? So where is this negative? When it's below the x-axis, which is from where to where? Between 2 and 3. So the answer to this question would be the interval 2 to 3. It's negative from the interval 2 to 3, when x is between 2 and 3. Now, how did I know that? Because I knew what the natural log graph looked like. I knew that this was a shift 2 to the right. And so I was very quickly and easily able to answer that question. Okay? So it comes in real handy. Otherwise, could you have just thought about logs and what values are going to make that negative? I think that would be a hard question. But if I could look at the graph of it, I think it becomes a very easy question. All right, so that's just one example of why we want to know, another example of why we want to know what these basic graph looks like. Okay, then we get the trig ones. If you look in your book, the last one they talk about are the trig ones. Now, we're going to spend a lot of time tomorrow talking about trig ones. For right now, just if you know your basic sine, cosine, tangent, you should be able to answer the question. All right, so last thing. Other, sometimes they're called power functions, other algebra functions. Okay, 2 quick examples. X to the 1/2 and 1 over x, which would be x to the negative 1. So x to the negative 1 or x to the 1/2, which of course would be the same as square root of x. Well, square root of x is just the top half of a sideways parabola. The top half of a sideways parabola. If you remember, sideways parabolas was x equals y squared, right? X equals y squared. Square root of both sides, you get plus or minus square root of x. Plus would be on the top half, negative would be on the bottom half, just like the circle. So the square root of x function is that. 1 over x is one we've talked about already this year. 1 over x does that, has some asymptotes, vertical and horizontal. Yeah, I mean, and they're just other ones, 1 over x squared. I mean, just other types of things. These do not count as polynomials because you can't have negative powers, you can't have fractional powers in a polynomial. So those are just other types of functions that it's good to know about. All right, so your homework for tomorrow is 1.3. Any of the graphs that they give you, you can go ahead and use your calculator to graph. Use those pictures then to help you answer questions about domain and range and what roots and whatever other kind of questions they ask about that. Okay, tomorrow we'll review what we need to know for the quiz and do a bunch of trig review also. All right, 1.3 homework for tomorrow.